Okay, so last time I told you sort of the axioms of theory X as far as we understand them, as far as I understand them. And one of the axioms in particular, somehow the most complicated one, was this statement that if you take theory X and you compactify it on a circle, so last time there was the statement that if I take theory X and compactify it on a circle, that this theory looks in the low energy limit. And here by low energy, what I meant was that we look at energy scales which are less than 1 over r. R is the size of this S1. Like a sort of conventional, well-understood quantum field theory, which is 5-dimensional super Yang-Mills. Okay, so I tried to say last time what low energy limit means. It means it's an approximate description, not an exact one, although for some quantities it might be accidentally exact. Okay, so, but what I didn't get to is anything about the Hitchin system, which is the thing I really want to understand. So let's do the thing which is going to lead to the Hitchin system, which is to compactify not on a circle, but rather on a Riemann surface. So we're going to go down to this entry here. So let's fix. Yeah, sorry. So let C be a Riemann surface, or in fact, initially it's not a Riemann surface. It's just a Riemannian 2-manifold. Actually, that's important. Not just a Riemann surface, a thing with an actual metric. So it is possible to compactify theory X on a 2-manifold in such a way. So I told you that there are some choices involved in general in formulating what you mean even by the compactification of the theory. But here, there's a kind of nice way of compactifying theory X on a 2-manifold in such a way that the resulting theory. So what does it have? So first of all, it has 4-dimensional Poincare invariance. So we started with a 6-dimensional thing. We've compactified. We made 2 of the dimensions into this 2-manifold. So there will be 4 dimensions left over. So it has. The 4-dimensional Poincare invariance, ISO 3,1 invariance. But it has more than that. It also has this odd extension, this n equals 2 supersymmetry. And a little more than that is true. Okay, so that's one thing you can do, and that's still, just as for the circle, that's still an incredibly complicated theory. It has that theory certainly has no simple description. But now again, we can look at a particular limit of it. And in this case, the simple way to describe that limit is in the limit. So in the limit where we rescale the metric of C, say the metric of C to t times the metric of C, and take t to 0. So we have like a family of quantum field theories depending on the metric on this internal space. And in the limit where we take the metric of that space to be very, very small, so we have kind of a family of quantum field theories, and that family is supposed to have a limit. So the limit as t goes to 0 of x of C with the metric Tg exists. And moreover, in that limit, it forgets a lot of the structure. It doesn't know about the whole metric. It only knows about the conformal class of the metric. It depends only on the conformal class. The conformal class of the metric. Let's see. So in other words, it only depends on C as a Riemann surface.
The statement that the limit of a
Yeah, so for example, I mean, it means that sort of, any reasonable quantity that you can formulate. So for example, take some correlation function of local operators. And yeah, I mean, here, since the theory is formulated in kind of a uniform way, I think I could make sense of what I mean by taking the same local operators, right, and taking the scaling limit. And then the statement would be that those correlation functions, for example, converge. Yeah, so in this limit, the theory is supposed to exist. And moreover, it only depends on the conformal class of the metric. In other words, it only depends on the Riemann surface. OK. Now, so this is what we call the theory of class S. And what can we say about this theory? So now that's supposed to be a 4-dimensional n equals 2 supersymmetric quantum field theory. What can we say about it? Well, so one thing we can say is that the observables, so much like we had in going from the 6D theory to the 5D super Yang-Mills, we can kind of match up the observables. So observables in the theory XG, so line operators, surface operators, local operators, will give us observables in this compactified theory. So for example, so I told you about a bunch of local operators in the theory XG. And those will map to local operators in the compactified theory. A little more interesting is suppose we consider the surface defects, surface operators in XG. Well, sorry, what was the picture for the local operators? Maybe I should say. So the picture was we have this internal space which is being crossed with R3, 1. So here's C cross R3, 1. We have the local operators in XG. And now we can imagine inserting those operators, inserting one of those operators at any point of C. Now for each choice of that gives me a local operator in the compactified theory. It's a different local operator. So I'm getting here a whole pile of local operators labeled by the points of C. OK, that's fine. As it'll turn out, they'll obey a lot of relations, so it's not as many as you think. But similarly, if I have a surface operator in XG, well, that can map to, actually, that can give me a bunch of different things. So for example, so one thing that could give me is it could give me a surface operator in the lower dimensional theory. How do I get that? Well, it would be, so in the 6D theory, I have a surface. One thing I'm allowed to do is take that surface to be just a point in the internal space cross a plane in, well, cross any surface, in fact, in R3, 1. So here I guess I had a point in R3, 1. Here I put on a surface in R3, 1. So that would give me a surface operator in XG of C. So this theory will have in it surface operators. Or we could also get line operators in XG of C. How will I get a line operator? Well, to get a line operator, what I would do is take my surface and take sort of one dimension of it to be wrapped around some loop in the internal curve, and then I'll have then I could have a line in R3, 1. And similarly, if I take my surface and just wrap it on the whole internal C, I could get a local operator in XG of C. OK. So a priori, I don't know much about this quantum field theory, but one thing I do know is it has a bunch of operators that come from the operators of the higher dimensional theory, just wrapped around the various possible cycles. OK, so I didn't say that they're supersymmetric. So whether or not they're supersymmetric depends on, so let's see. So what is the story? So yeah, I think in fact all of these do give you supersymmetric operators in the lower thing. And in fact, yeah, I may as well say it now. So by analogy to the statement that the whole theory depends only on the conformal class, there's a similar statement about these operators. You might ask, for example, if I have this line operator, right, that's wrapped around some loop, and does it depend on every little detail of the loop? Well, in the full theory, of course, it does. I mean, the thing is at a definite place. But once you flowed to the, once you take this limit where you shrink the thing to 0, the statement is supposed to be that it depends actually only on the homotopy class of that loop. So we're going to have operators, yeah, this will be important at the very end, I hope. So we're going to have operators which will be labeled by homotopy classes of paths in the infrared limit. In the limit where we shrink this thing to 0 size. OK, so maybe the only other thing to say about this theory. So we're getting some quantum field theory by this construction, some quantum field theory which depends on the data of a Riemann surface.
Why do you not worry about, that, like, I have to say, I would have like no concern with something like free homotopy class of path. I mean, that you allow the paths to cross each other, and that's just totally okay.
Oh yeah, no, okay. I mean, yeah, that's a good question. So people have. The case of having these things cross each other hasn't been investigated so thoroughly so far. So indeed, what people usually consider non-self-intersecting and mutually non-intersecting paths. Yeah. OK. So so I told you that there's some four-dimensional quantum field theory, and you could ask, is it equal to some kind of conventional quantum field theory that I've heard of before? And the answer is usually not. So, so for a general choice of C and Lie algebra G, so this quantum field theory that we're talking about, this quantum field theory xg of C, is not, as usual, it's a time-dependent thing. So it's not known to be Lagrangian. On the other hand, sometimes it is. And when it is, that's often very, very interesting. That's a very useful thing. But from my point of view, in these talks, for the most part, I'm just going to ignore this fact. So even though it occasionally has a Lagrangian, I won't use that Lagrangian.
Andy?
Yes?
Why didn't you put the four-dimensional?
I'm sorry?
You also have four.
Yeah, no, that's right. We could have also talked about what the four-dimensional operators do. That'll give you yet more stuff. So I was just... that's right. So that can give you like domain walls, or it can give you another kind of surface defect when you wrap that thing on the whole internal curve. OK, so now still in saying all this, I haven't yet got to the Hitchin system. So where is the Hitchin system going to come in? The Hitchin system. So the Hitchin system is going to arise when we make one more reduction. So so we can also consider, again, take this theory X and compactify it. Now we compactify it on the product of a Riemannian two-manifold and a circle. So this theory, and again, I'll compactify it again in a slightly clever way, so that we get a theory which has supersymmetry. So now it's going to be a three-dimensional theory that we're going to be left with. And that three-dimensional theory is going to have, so in the same notation as Tudor's talk, n equals 4 supersymmetry in 3 dimensions. So it's the same general class of theories that Tudor has been talking about. And we want to describe as precisely as we can this theory, and particularly its local operators. So what can we say about it? Well, we're going to have actually 2 different perspectives on this. Yeah. Yeah.
Is this new thing you're doing factoring through yesterday? I mean, is this theory a compactification of 5D super Yang mills?
So there are 2 different perspectives on it.
Oh, okay.
One of those perspectives is essentially what you just said. So no, it's perfect. So there's sort of 2 different regimes in which we could study it. One is the regime in which the size of the circle is taken to be somehow much, much smaller than the size of the surface C. And the other is to do the other way. So size of the circle much, much bigger than the size of C.
I thought the size of C was already like 0.
No, so OK, it's possible to take that limit. And if you take that limit, then you get the quantum field theory. Then you get the sort of simplified quantum field theory that I told you about. So I mean, yeah, OK. So there's a notational thing. So when I write xg of C, do I mean like the 0 area limit of the theory, or not? So yeah, I guess here when I've written xg of c. Yeah, let me, to make that clearer, I'll put a 0 here. I mean, this is the 0 area limit. I guess that's right. And if I don't write that, I'm not talking about taking like the 0 area limit. I'm thinking of the thing as being potentially of finite size. So of course, things will be simpler in the limit where we do take the size of c to 0, but in principle, we don't have to. And so when I compactify the thing on C cross S1, there's sort of two different perspectives I could have. I could think of, so for sort of random sizes of these, there's essentially nothing I can say. But in this limit or in this limit, there is going to be something we can say. Now, the remarkable thing.
But you don't require then both of those to be extremely small. That's not extremely small in that order? Or?
Well, yeah, I mean, eventually, that's right. We're going to take them both to be small. Yeah, so maybe it'll be clearer as I go. So what's remarkable, and so I'm going to tell you sort of what would be guaranteed on general physical principles in either of these limits. And the remarkable thing that seems to be true, which is a kind of topological field theory-like property, is that it seems that, so we'll get some insight from considering this limit, some insight from considering this limit, and remarkably, it seems that although a priori they apply to different regimes, actually you can use them both at once. So both perspectives. So a priori, they're derived in these special limits, but actually you can use them both simultaneously. So they work even outside of the sort of naive domain. So I think this is something sort of similar to the thing I told you a second ago, that in the limit where this Riemann surface where this is taken to be small, everything is independent of the precise conformal factor. So here it seems that we're saying that that's true even with this circle in. So yeah.
You look at BPS
Yeah.
quantities, they might not depend on these quantities.
That's right, but what I'm saying, it's going to be stronger than that. I mean, it's not only about BPS quantities. I mean, much like this statement here, which is the statement that the theory is independent of the conformal factor, that is not only a statement about the BPS quantities. That's supposed to be a statement about the whole quantum field theory. So it doesn't seem to be something which follows somehow sort of directly from sort of simple kind of topological field theory thinking. Okay, but nevertheless, it seems to be true. So let's look at these kind of two different ways of thinking about the thing. So let's first look at the limit. So let's look at C cross S1 with the size of C much smaller than the size of S1. Oh, sorry. With the size of S1 much smaller than the size of C. So in that case, we might think of it in the following way. We might think that what we first do is we take the six-dimensional theory, compactify it on this circle, look at everything, look at low energies, so look at everything small compared to 1 over this radius. And then, as a further step, we're taking that 5-dimensional theory, and then we're compactifying that 5-dimensional theory on that Riemann surface. So let's take that point of view. What we have, so again, it's approximate, but as long as we stick to energies that are low compared to 1 over this radius, and we're taking that to be very, very small, so essentially, we can just think that what we have is really the 5-dimensional super Yang-Mills now, and we're compactifying that 5-dimensional super Yang-Mills on C. Let's study it from that point of view. So you remember the fields of 5-dimensional super Yang-Mills. We had the gauge field, so the connection D equals D plus A. So A was one of our fields, and the other fields were phi 1, phi 2, these scalars, all adjoint valued scalars, phi 4, and phi 5. Now this is what we have in when we formulate the theory in flat space. Now we're compactifying it on the Riemann surface. When we compactify the theory on the Riemann surface, we make a little we make a little change to the field content. So we think of these, instead of thinking of them as just being 5 scalars, we combine these two into a complex value. So first of all, we combine them into a complex thing. And second of all, we combine them into a complex valued one form on C. So you think of it as phi. So if you like, it's phi 4 plus I phi 5. Easy. Well, this is in the theory on C. So when we formulate the theory on C, we describe the fields slightly differently. So we describe them as a connection, 3 scalars, and now one complex valued adjoint one form. Yeah, so the SO5 has been broken. That's right. So this compactification process. So I told you that there's some choices involved. There's some choices involved in the compactification. And one of those choices, in fact, is the choice of a division of that 5 into 2 plus 3, if you like. So the SO5 R symmetry, which was there in the original theory, is explicitly broken by this compactification.
This is surprising, right? Because the 5 is 11 minus 6. The transverse dimension is the M5 ring.
Right.
Now the M5 is like happens to be written as a Riemann surface times something. Why are
Right.
those 5 transverse dimensions? Which ones of those have to do with C?
Yeah, the thing is that the background in which you put the thing. So if you took the geometry to be literally like R11 or R10, 1, and you put some curved surface inside of that, from the M theory point of view, that would not be a supersymmetric thing to do. What is supersymmetric is to put it in a background where 4 of the directions are the cotangent. So you put it inside of a hyperkähler manifold. You put it inside the cotangent bundle of C, and then some of the extra directions are cotangent directions. That's this. The others are flat. Those are those. So that's how that twisting would sort of arise from the M theory point of view. But for my present purposes, I just say compactify the theory to make this twist. OK, so now what's the question we want to ask? The question we want to ask about this theory is the same question that we asked about the theory compactified just on the circle. The question is, what is the low energy physics of this theory? So how to describe the physics of this theory? At low energies. And so here, what I mean by low energies, I mean low compared to the scale of this Riemann surface. So sort of typical scale of the Riemann surface. So in general, that kind of question is hard, but in this case, it's actually not so hard. So there's an important fact which Tudor mentioned in his talks, which is that the way a quantum field theory behaves at low energies depends a lot on what dimension you happen to be in. And Super-Yang-Mills in 5 dimensions has the nice property that it's so-called infrared free. In other words, if you look at questions, sort of long-distance questions, such as this question, what's the low energy physics? The classical approximation is supposed to be extremely good. So in general, you can't just answer this kind of question by purely classical considerations. But in this particular setup, exactly the way we've set it up here, we can use classical field theory to answer this question. And so you might start out by asking, the simplest question you might ask is, what are the actual vacua? Now, what is a vacuum? So vacuum, in this situation, we're looking at a theory which is going to be effectively 3-dimensional. So we ask, so the first thing we might ask is, what are the classical field configurations which preserve the ISO. So now we have ISO 2, 1 symmetry. In other words, they're invariant under the translations in the remaining 3 directions. And let's also ask them to preserve the supersymmetry, so the supersymmetric ground states of this theory. And then you ask that question, just a purely classical field theory question, and the answer is, well, everything is going to be invariant in the everything is going to be invariant in the R3 directions. We're just left with something depending on C. And the dependence on C is that, so first, actually, for simplicity, let me first assume that these fields are 0, and we'll come back to that in a minute. So assuming that phi I is 0, in other words, phi 1, phi 2, and phi 3 are all 0. So then what do I have left? What I have left is a connection plus a complex valued 1 form. And the equation that they turn out to satisfy is this equation. So two equations. One is that the curvature of the connection should be equal to the bracket phi with phi dagger. And the other is that phi should be covariantly holomorphic. So here are the two equations that you get.
Wait, what is this bracket operation?
So phi was a complex. So these things are all valued in the adjoint. So these are all G valued, Lie algebra valued. And so the bracket is literally just the bracket on, I mean, the bracket of 1 form is valued in the Lie algebra. So this is going to make, so this is a 1-0 form valued in the Lie algebra. This is a 0-1 form valued in the Lie algebra. And so what we're going to get is a 1-1 form valued in the Lie algebra. And the curvature of this connection is also a 1-1 form. So here are the equations. So you just get them by studying this 5-dimensional Super-Yang-Mills theory. And on the other hand, these are kind of so these are famous equations.
Is the second sentence of that board on the right, the precise formulation of that is that the moduli space of classical vacuum does not receive quantum fractions? Is that how I should
Right. That's exactly how you should think about it. Because it's it's a really peculiar thing to 5-dimensional gauge theory. Had it been 4-dimensional gauge theory, as I hope we'll say, it would not be like that. But because
that's the takeaway.
Yeah, and that was peculiar to the fact that we took this limit where we took the circle much smaller than the curve in order to get that simplification, right? It's important that we're effectively in 5 dimensions. It's a high enough dimension that this kind of thing works. So what are these? So what's the meaning of these equations? So let's call these equations star. So star are these famous equations, Hitchin's equations. And so we look at these, the vacua of this quantum field theory are solutions of these equations modulo gauge. So as usual, this is a gauge theory, and so we always look at everything modulo gauge transformations. So let's say it this way. So the space of solutions of star modulo gauge transformations so let me call that MC of G. So this is the Hitchin's integrable system. Hitchin's let's call it Hitchin's integrable system. But so far we just see it as a manifold, right? Just the space of solutions of this equation. And so this is the moduli space of vacua of MC xg C cross S. So as I say, so okay. So what does it mean to say that that these are the vacua of the theory? So for example, it means the following. Suppose that I wanted to compute something in this theory. So we're in a 3-dimensional field theory, which we say has this choice of classical vacua. Now, so if we compute, for example, say correlation functions of this theory, xg of C cross S1, so I have to tell you what to do with the remaining 3 directions, and suppose that I take the remaining 3 directions to just be R2, 1. So then, you can see that those correlation functions. So the correlation functions are not going to be just numbers, but rather they're going to be functions on the moduli space of vacua. So what we get is, so any particular correlation function, what we get is a function on this moduli space of vacua. Why is that? So one way of seeing it is we're in this regime where classical field theory is pretty good. So one thing you could say is that to formulate the path integral, we need, so we're doing a path integral in this non-compact space, and we need to fix some boundary condition for the fields. You take a boundary condition that these fields d and phi should approach some fixed point d naught phi naught on the moduli space of vacua. And so whenever you compute anything in this theory, this is the same point that came up in David's talk this morning. Whenever you compute anything in this theory, what you get is not just a number, but what you get rather is a function on this moduli space. Yeah.
Sorry, I think I missed some step between dimensions 5 and 3.
Yeah. Okay.
I can sort of, with a 3D theory, I sort of know what vacua are in 3D, at least for supersymmetric theories.
Mm-hmm.
And so I said that all sort of, like, so I can probably convince myself that sort of vacua on the 5D, like if I think of the C as sort of having some small but positive size,
Yeah.
that those would all kind of give me vacua in the 3D theory. I guess I don't, you had some equation that had something to do with sort of the C directions, and I don't see where those would be coming from like a vacuum, being a vacuum just in 3D. Am I making sense in that question?
Let's see. So our notion of vacuum here was something which preserves the three-dimensional.
Right. So 3D symmetry.
Yeah.
So how did you get any sort of equations like for the curvatures in the C direction?
Oh, sorry. So, that's right. So we asked for it to not just to be not just to preserve the 3D symmetry, but also to be supersymmetric, to preserve the supersymmetry. And yeah, that's actually enough to get this equation. Yeah. Sorry.
So what was up with phi 1 to phi 3? Why did you have to set those?
Oh, why did I set them to 0? Great. So there's also equations on phi 1 and, to phi 3. That's right. So remark. That's right. So I said this is the whole moduli space of vacua. It's actually not precisely true. So these were all the vacua where I set those fields phi 1 up to phi 3 to 0. So the supersymmetry also imposes equations on phi 1, phi 2, and phi 3. Yeah, let me write those equations. So the equations say that d phi I is 0, that the bracket with the Higgs field is 0 for all of them, and that the brackets of the phi's with each other, bracket of phi I with phi j, is 0. And if you look at these equations, so these are some equations which depend on where I am with the fields d and phi. In other words, where I am on this moduli space. And if you're at a generic point of this Hitchin moduli space, these equations won't have any solutions. And so saying phi equals 0 was, in that sense, kind of a consistent thing. Even if I had even if I allowed these equations, I wouldn't have gotten anything new. On the other hand, for example, if I went to like the trivial connection where d was just trivial and phi is 0, then these equations really would have solutions. And so the actual picture, that's right. So the full moduli space. So really the correct thing to say is that this is one branch of the moduli space of vacua. It's the branch in which we're somehow most interested, but the correct picture of the moduli space, indeed, so the full picture of the moduli space is it has, roughly speaking, one branch, which is this Hitchin moduli space. I'll carry on calling that MC of G. And then sticking out from some special points, there may be other branches where these equations admit solutions. And so those other branches, so this MC of G is usually called the Coulomb branch. And these other branches are called mixed branches or Higgs branches. Okay, so for me, that'll just be terminology, but you'll see actually this feature of that the moduli space has sort of multiple branches of vacua. That feature is going to be very important in Tudor's talks.
So algebraic geometries are branches irreducible components?
Sorry, say it again.
Are branches irreducible components? What are branches?
So, yeah, I mean, that's how you should at least loosely think of it.
No one promises you to use
Okay, that's fair.
They're certainly not connected components. That would be
That is true.
Yeah. No, I think I better not try to say anything sharper than what I said.
some like natural stratification of the space of just divided physics.
Okay. So I mean, one thing you can say is that yeah, I mean, one way of distinguishing the different branches is by looking at how the R symmetry. So Tudor talked a little about the R symmetry of the theory, and one way of distinguishing the different branches is to look at how the R symmetry acts on the different branches. But let me not try to.
So how many branches are there?
What's that?
How many branches are there?
There may be a lot. So depending on the, I mean, you know, a finite number, I suppose. But depending on the theory, there may be quite a lot of branches.
Are there theories where you know the answer?
Yes, I mean, for example, for you know, there's some theories where there's only the Coulomb branch and no Higgs branch at all. So yes, there's some where I know, but in general, there's not a whole lot that I can say.
things that the mathematicians call Higgs bundles, the ones that live on the Coulomb branch.
That's right. Sorry, that's just a fact. That's just a fact. So the moduli of Higgs bundles is the Coulomb branch of this. That's exactly right.
How to say, is that some sort of historical mistake? Is there a reason why we say that?
No, I mean, it's a funny thing that, yeah, I mean, indeed, you know, the symmetry is broken. In physics, it's also funny because the Higgs mechanism occurs on the Coulomb branch. Yeah, I mean, I don't know what, yeah.
Do the branches have different dimensions?
The branches certainly have different dimensions. That's right. That's right. Okay, so what I've sort of,
This whole moduli space, I mean, the moduli of Higgs bundle has a complex structure, maybe many of them.
has a hyperkähler. Yeah.
Together, is that true of the?
Yeah. So in this, in the setting that I'm in now, all of these branches are actually hyperkähler. So I can't usefully distinguish them by.
Cool. My real question is there an algebraic geometric question you can ask whose answer is that whole moduli space? Instead of the usual question which we ask, whose answer is moduli of Higgs bundles.
Well, in this setting, I think I could say that it is the. I think I could say that it's the solution space of this full system of equations that I wrote.
Yeah, but is it obvious from the equations you wrote that should be an algebraic question?
Oh no! So I'm not. I mean, maybe someone knows, but I don't know. I've never thought about that.
Don't you just look at
the boundary conditions. So you
Yeah.
the boundary conditions where the D and P approach some fixed values that approach.
Right. Approach on. So right. So we're doing the path integral on R2, 1. So the picture is that you're trying to compute a correlation function of this theory, and you're trying to compute it where the non-compact, where the three-dimensional part, so the full six manifold, if you like, is C cross S1 cross R2, 1. And so we have to fix boundary conditions at the asymptotic infinity of the R2, 1. That's a sort of rough way of thinking about why the correlation functions in this theory depend on a choice of a point of this moduli space. It's just because you compute path integrals with some asymptotic boundary condition. Okay, fine. So all I've told you so far is that this theory, this theory xg of x cross S1, yeah, it has a moduli space which includes as a piece this this Hitchin moduli space. Now you can say a little more, but I'll have to say it quickly now. So I didn't tell you the whole low energy description of the theory. What I promised you was to tell you exactly what the theory is at low energies, not just what its moduli space is. So I'll just tell you the statement. The statement is that the low energy physics of theory X formulated on the space. So now low energy compared to everything, compared not only to the circle but also to this Riemann surface. So this is like the limit where now I'm taking everything to be small. So you asked, are we at some point going to take everything to be small? Yes, now we're taking everything to be small. We just did it in a kind of ordered way, where first we took this small, and then we took this small. And what we're getting is actually a theory called a sigma model with target. Well, it should really be the whole moduli space, but let me focus. I'm just focusing on what's happening around a point of the Coulomb branch. So I'll just say a sigma model whose target is the Coulomb branch. So what does that mean? It means it's a field theory. So this is the kind of field theory that you can really describe by fields. Fields. So the bosons are just maps from, call the map sigma, from R2, 1 into this moduli space. And then in addition to that, it has some fermions. So it's not only a sigma model. So it's a sigma model, but it was supposed to be a supersymmetric theory. We said that it should have n equals 4 supersymmetry. And the n equals 4 supersymmetry in this context, what it requires is that, so as part of the definition of the sigma model, this thing is supposed to have a metric. And that metric is going to be, so supersymmetry requires that the metric on MC of G should be hyperkähler. Of course, that's fine. We know that the Hitchin moduli space does have a natural hyperkähler metric, and sure enough, that's the metric that you get.
This low energy physics statement, is there a reason that you've been told to ignore the other branches?
No, I mean just because most of what I say will pertain to this branch.
What does that mean when you like the energy physics of this theory?
Well, so right. I think a slightly more precise version of what I've said here. Yeah, a slightly more precise version of what I've said here would be the following. So choose some particular point. So we're going to, when we study this theory, when I ask the low energy physics, it's always the low energy physics in a particular vacuum. And so suppose I choose some vacuum, which is, I could choose a vacuum anywhere, but suppose I choose a vacuum which is lying on the, Coulomb branch at some point. Then, as long as I look at low enough energy, and how low the energy has to be will, I think, depend even on where I am relative to where some other branch emanates. As long as I look at low enough energy, it'll be accurately described by a sigma model which only uses this branch. Yeah, so that's a slightly more precise way of saying what I'm saying here. Okay, so now, the idea now is that we would like to understand this space. We would like to get some new information about this space from this point of view. How are we going to get new information about this space? The way that we're going to get it, is to think about this theory, the same theory now in the other way. So, so we want to understand this space better. The way we want to understand it is by viewing this theory, xg of c cross S1, now as the compactification of, so now we start with this theory, this four-dimensional theory, and compactify it on S1. In other words, we take the limit, so I called this SG of c comma 0. So now we're going to take the 0 area limit first for this curve C, then compactify it on a circle, and then look at low energies relative to the scale of the circle. So this is kind of the opposite limit from the limit we were in before. So now we're taking the size of C to be much, much smaller than the size of the circle. So let's try to understand that. In order to understand that, we have to first understand the low energy physics So we want to understand the low energy physics of this compactification with things set up in this order. To do that, we have to first understand the low energy physics, low energy description of xg of c itself. So the picture is going to be the following. Well, yeah, let's just say it like this. So we first want to understand the low energy physics of this 4-dimensional theory. And then after we understand that well enough, we're going to compactify that theory on a circle. OK, so let's try and understand what this 4D theory is like at low energy. So much like the 3D theory that we just talked about, this theory xg of c, again, when you ask about its low energy physics, the question doesn't have a single answer. The question depends on where you are on the moduli space of vacuum. So just like the 3D theory, this 4D theory has a moduli space of vacuum. So the answer to any question in this theory is not going to be just a number. The answer to any question in this theory, formulated on R 3, 1, is going to be a function on this moduli space of vacuum.
Do you understand more or less correctly that usually determining the moduli space of vacuum is a mathematically well-defined and question, which has a sort of an answer, which is a theorem?
I mean, in any particular example, we can usually formulate what it means. But I mean, since at least I don't have a fully general definition of what a quantum field theory is, right, including all non-perturbative. In order to determine this moduli space exactly, you have to understand all the non-perturbative phenomena as well as the perturbative ones. So because of that, I don't think that I could formulate. Maybe some people can, but I would not be able to formulate mathematically exactly what this question means. I can formulate it physically. It's literally the question of, it's part of the question of describing what the low energy physics of this theory is to say what are the possible vacuum states that it can have.
So what is wrong with the description this morning of the spectrum of the local operators?
Okay, so that sometimes works.
We already said this morning what was wrong with it. It was affine, and moduli spaces aren't always affine. And Devin said somebody to fix that up, and maybe we'll see more of this tomorrow.
Well, there's the question of whether you consider all local operators or only the supersymmetric ones. If you consider only the supersymmetric ones, then we'll see in a second an example where that's not good enough. If you consider all local operators, then perhaps it's true that you can distinguish where you are anywhere on the point of.
I'm pretty sure if you only supersymmetric, how they would have few fixed points in the moduli.
Well, yeah. So I mean, so if the theory itself is supersymmetric, okay. First of all, you consider a theory that's not supersymmetric and ask the question. So then obviously, yeah, I suppose that's right. If the theory is not supersymmetric, then there's.
I mean, on the other hand, in these IAS notes, 1996, within saturation quantum field theory has a definition of vacuum.
Yeah.
Which is something that gives an operator a number of which, when you separate them far apart, it separates them apart. So, I mean, I think it is. If you look at the chiral rings, this is exactly the spectrum. But in general, it's not a homomorphism. It's only a homomorphism as we comprehend.
Okay, so that's like defining it by the 1-point functions, right?
No. You can take any collection of local operators.
The 1-point functions of all local operators.
No, the endpoint functions.
Oh, take all the endpoint functions.
All the endpoint functions with the property that when I separate them far apart, it factors.
Okay, I think I don't have. I don't immediately have a useful.
I'm just quoting Whitman.
Yeah. Yeah.
It's not a homomorphism, but it's something similar. It's not a computer operates.
Okay.
Something like Ferguson.
We have a Lagrangian description as a well-defined moduli space of classical vacuum.
Right, but that may not be what this is. So for.
Then there's some quantum corrections, which.
That's right.
Something about that process, because I don't think I know what it means to like quantumly correct the moduli space of vacuum.
Right. So I mean, that's in general that's in general not an easy thing to describe. You know, what are the exact quantum vacua of the theory? I mean, I don't think I can say anything simple in general about it. So, I mean, well, we'll see an example. We'll see an example in a second. So I'm going to tell you what this moduli space of vacua is in this particular example. So yeah. So let me say. So the local operators. So let's study this particular theory. Take theory X with a Lie algebra G and on a Riemann surface C. Say the C comma 0. So, well, sorry. Yeah. Let me just say what it is in this case. So again, it's going to have a bunch of branches. I want to focus on one branch, the Coulomb branch. And what it is simply the Hitchin base of C. So what does that mean? So for example, just to be concrete, so it's the base of Hitchin's integrable system. But for example, if G is A, K minus 1, this B is just the direct sum over index R going from 2 to K of H0 of AC. So in other words, in this particular case, it's a complex affine space, a complex vector space. And it comes endowed with a bunch of structure. So I'm sorry, I'm not telling you how to calculate it. In fact, we'll get it kind of indirectly. In this particular example, the way you get it is essentially to use this extra compactification on a circle. Because we did see that the moduli space of the three-dimensional theory was the whole Hitchin integrable system. And from that, we can actually sort of back compute that this one is the Hitchin base. So let me just describe some of the basic structures that it has and sort of its key property. And then I guess I'll quit. So the Coulomb branch. So I'll give you here the sort of physics words. There's the Coulomb branch, which has in it singular locus. At any point of the Coulomb branch, there's an electromagnetic charge lattice. And there's some distinguished functions, which are called the central charges. So what are the structures that they carry in a general n equals 2 theory? The Coulomb branch is supposed to be a complex manifold. So in 3 dimensions, it was hyperkähler. Now we're studying a 4-dimensional theory, and so this Coulomb branch now is a complex manifold. It's containing some distinguished divisor. So let's call this complex manifold B. It's containing some distinguished divisor, B singular, inside of B. It has a local system of lattices. Gamma over the regular part, so B minus B singular. And it has these distinguished functions, these central charge functions. So at every fiber of this, at every point of this Coulomb branch, there's a lattice and a homomorphism from that lattice into C. So it's a fiber-wise homomorphism. And it varies holomorphically over the Coulomb branch. And what are they in this particular example of the theory of class S? So as I said, the Coulomb branch is just the base of Hitchin's integrable system, the Hitchin base. The singular locus is just the discriminant locus of the Hitchin base. So at each point of the Hitchin base, there's a corresponding spectral curve, and this is the locus where the spectral curve becomes singular. So this is the locus of singular spectral curves. This lattice, the lattice of electromagnetic charges, in this case is going to be the first homology the first homology of the spectral curve with z coefficients. And the central charge functions are going to be periods of the spectral curve. So yeah, so over Hitchin's integrable system, so sigma u is the spectral curve sitting inside of the cotangent bundle. So for example, at the point, so if we're in the AK case again, if we're at the point phi2 up to phi k in the Hitchin base, the spectral curve is given by the equation lambda to the k plus some 2 to k of phi r lambda to the k minus r equals 0. Okay, so we have this. So the mathematical structure is you have this complex manifold with a local system of lattices over it, which are just the homology of some family of curves. At some particular point, the curve degenerates. Those are the singular points. And we're going to keep track of, in order to understand the low energy physics of this theory, in order to understand the low energy physics of this quantum field theory, as it turns out, all we need is this family of curves. And more precisely, what we really need is not so much the family of curves as the family of their homologies, these lattices, and these central charge functions. That turns out to be enough to completely describe the low energy physics of this theory. Let me say it a little more precisely, and then I'll stop. I'm sorry, I'm already a little over. So the key statement is the following, to which we'll return, I guess, at the beginning of the next. So, and this is the thing that was discovered and exploited by Seiberg and Witten, very famously. The key point is, for any n equals 2 supersymmetric field theory on its Coulomb branch, in particular for the one that we're studying, but this is actually a general picture. So if we're in this, this good part of the Coulomb branch, in this case means away from the discriminant locus of the Hitchin fibration. So remember, every point of this is supposed to be some possible vacuum of this quantum field theory. That's how we interpret the Hitchin base. And the statement is that if you're at a generic point, the low energy physics well, below some scale, I'm not telling you, well, yeah, I may as well say what the scale is. Lower than the minimum, you can actually be pretty precise about it here. So lower than the minimum value of absolute value of z gamma. So we have these functions z gamma, and those z gammas are, among the things that they do is they kind of measure how good your low energy approximation is. So as long as you're below all of those numbers, the low energy approximation is going to be good. So I mean precisely this. The low energy physics is given by a very simple quantum field theory, just 4-dimensional supersymmetric Yang-Mills. So just like the 5-dimensional super Yang-Mills that we wrote the other day. That would be generally complicated, but here it's abelian. The gauge group is just U1 to the R, where R is the dimension of this Coulomb branch. So this is, no matter what n equals 2 supersymmetric field theory you start with, you look at it on its Coulomb branch, it turns out to be just governed by abelian gauge theory. Abelian gauge theory fibered over this complex manifold, which in this case is the Hitchin base. At these special points, at the discriminant points, so one way of understanding the discriminant locus is the place where one of the cycles of this spectral curve shrinks. That corresponds to one of these z's going to 0. So exactly when you go to one of those points, this low energy description is getting sort of less and less good. You have to go to lower and lower energies. And as you get right to exactly to this point, it becomes useless at any energy. And so at these points, you need something more elaborate. OK, well, so I guess that'll have to do. So the next thing, of course, the thing to which we've been building up is to take this description now, to take this interpretation of the Hitchin base, compactify that thing on a circle. Now, from what I told you last time, from this totally other reasoning involving theory X, what we get at low energies is supposed to be a sigma model into this Hitchin space. But But when we study it from this perspective, we're going to learn a lot more about the Hitchin space than what we usually say. OK, so that's the aim. Thanks. Yeah.
Is that discriminant locus also the point at which these other branches, the mixed branches and mixed branches are emerging?
Yeah, so if they emerge, I mean, it doesn't have to happen. So it's not like every point of the discriminant locus necessarily has a Higgs branch coming out. But when you do get a Higgs branch, yeah, it comes out from one of those places.
And could you in general say what parameterizes the central charges? It seems like we have a whole bunch.
So they're parameterized by, yeah, so sorry, I said it in a hurry. So so they're parameterized by, well, they're parameterized by this.
Yeah, like in this case, yeah. Like it's a cyclic gamma. But
Yeah.
in general for a theory, is there some kind of guy that parameterizes the central charges of a theory?
Oh, for a sort of random theory? So I mean, yeah, I mean, right, so this is all sort of general stuff that happens for any n equals 2 theory. This column, to tell you this column, you have to tell me first how you're giving me the theory. So for any particular way of describing the theory, there will be some description of what the charge lattice is.
No. Just we have a whole bunch of central charges. Like there's not just one Z. There are a whole bunch of Z gammas.
Right, that's right.
The group of gammas.
The group of gammas. Oh, gamma. It's the charge lattice. Yeah. So we have this.
Okay, sorry.
Yeah, it's exactly that. So we have just a lattice worth of them. Yeah. Right. What are the constraints on the central charges? OK, good. So indeed, they're not completely arbitrary. There is a constraint, and the constraint is what? So the sort of slick way of saying the constraint is that. So yeah. OK, good. So so this charge lattice. One thing about this charge lattice is that it comes with a pairing. It comes with an antisymmetric pairing. So in this case, you can see that because the first homology of a curve, of course, has an antisymmetric pairing. OK, so that pairing is part of the physics. And the constraint which these functions are supposed to obey is that if you look at, so suppose you look at dz. So this is now a one form that's valued in gamma dual. You could take dz. So take the wedge product of dz with itself, pairing with this antisymmetric pairing. So this isn't automatically 0 because the wedge product is antisymmetric, but the pairing is also antisymmetric. So this is a thing which potentially could not be 0. Potentially could be non-zero. The constraint is that it actually is 0. So yeah, that corresponds to the existence of prepotential from the point of view of the n equals 2 supersymmetric field theory. So that's right. So the z's that you get will always obey this condition. And sure enough, if you look at these periods, they do obey that condition. But that's the only constraint that they have to obey. Yeah.
Could you indicate the sort of arguments for why it doesn't matter which one we take to 0 first, the circle or the?
Well, I can't give you a really satisfactory.
How do people even go about arguing this sort of thing?
Well, so in this case, yeah. So as I say, I think it's essentially the same statement that. Oh yeah. OK. So let me tell you something that might help a little bit. So this is pretty similar to it's kind of an elaboration of something that I said earlier, which was that in the limit of small, the limit where you take this Riemann surface to be very small, the dependence is only on the conformal class. So you could say, how could you possibly know something like that, right? So that particular thing, there is an argument for it, and the argument actually comes from holography. So so it has to do with a sort of funny thing. It's the limit. So we have this Lie algebra AN. Let's do just the A case. And in the limit where n goes to infinity, this theory is supposed to be well described by us to have a sort of dual description involving gravity in well, in this case, so now we've compactified it, right? So it's not anymore ADS7 cross S4, it's something else. But anyway, it has some gravitational dual description. Now, in that gravitational dual description, there's a direction which corresponds to the energy scale. So there's a direction where if you go out one way, a long way, you're in the UV, and when you go out the other way, you're sort of going to the IR. So the question from that point of view is, suppose I put this Riemann surface, so this geometry, one of its factors is the Riemann surface. Suppose I put an arbitrary metric on that Riemann surface on one side, and I just solve the gravitational equations. What happens to that metric on the other side? And what these people showed, so it was showed by, it's bad, so I won't remember everyone. So Bobev, Beam, Anderson, but I'm afraid I'm missing one. Rastelli. Okay, so these are the four. So the paper is called holographic uniformization. So what they said was, suppose that in the UV you put an arbitrary metric, and then just solve the equations of the gravity theory and just see what the metric will do. And what they showed was that sure enough, it flows to the hyperbolic metric. So in particular, the dependence, so in the UV you can choose any metric, and as you flow into the IR, the dependence on the metric seems to be washed out.
Okay. So that's still an argument for the large N limit.
Yes.
You're saying it's probably true also.
I'm just saying that's the best evidence. So I mean, so the other evidence is that this is consistent with, there's many examples of field theories which we believe are realized in this way. And in those theories, there seem to be no other parameters. There's only the parameter that corresponds to the conformal class. There are not additional parameters that we know about. So that's also consistent with at least the idea that it only depends on the conformal class. It's that kind of indirect stuff. I mean, it has to be because this theory X is still not so easy to access. And I mean, it's not a statement just about supersymmetric quantities. It's a statement about everything. So it's hard to see how to get it by simple sort of TFT arguments. OK. So the statement that you're asking about the relative, that depends on the relative scales of C versus the circle, you could think of as kind of an elaboration of that. It's a statement that the metric on C doesn't matter even when you also put in this extra circle. So you can imagine trying to prove it by a similar kind of thing, actually, where you also put this circle in. Yeah, I mean, it's a little rough, but everything works. Everything seems to work out very well, so it's probably true. But, yeah.
The reason they call it branches is because there's like the one branch is kind of like a tree, and then there's some extra branches.
No, I mean, it really is supposed to be branches in the sense of, I mean, morally it's, I mean, what can I say? It is like having, it is like having xy, the look at xy equals 0, right? You would say this has two branches, right? The branch x equals 0 and the branch y equals 0. Yeah, they're like, I mean, I'm not swearing to it, but.
How generally is it true that the low energy description of the theory is a sigma model with target moduli spaces acting on?
Well, OK, so we saw that it was true. It might be always true in 3 dimensions. In 4 dimensions, we just saw an example where it's not true, right? The low energy physics of that theory was not a sigma model. It was, it does have a scalar in it, which you would think of as being the sigma model scalar, but it also has gauge fields. So the low energy description of that 4-dimensional theory is not a sigma model in the usual sense. It's just not. And in 2 dimensions, it actually never happens that.
But it's a sigma model into a stack.
OK, fine. So in 4 dimensions, it's a sigma model into a stack. But yeah.
Which is a gauge.
Right.
So it's always true.
Well, yeah, I can't say it that way.
That's what the word spec is supposed to mean. It's you define it tautologically. The space is now a stack.
I'm done.
Let's release.